In this lecture, what we'll be doing is we'll be taking a look at the second law of thermodynamics, and we'll be looking at the second law of thermodynamics as it applies to both heat engines as well as heat pumps or refrigeration cycles. So to begin with, what we're going to do is we're going to give a brief introduction to the second law of thermodynamics and what it does for us versus what we've already looked at, which is the first law of thermodynamics. So we'll begin by discussing the second law of thermodynamics. And our treatment today is going to be more of an understanding or conceptual one. The treatment in a subsequent lecture will be one more of a quantitative approach to looking at the second law of thermodynamics. So the second law, what it does for us is it is concerned with which the direction that energy will flow within a process. When we looked at the first law thus far, we've seen heat transfer, we've seen work, internal energy, enthalpy, kinetic energy, potential energy. The thing about the first law is that although we are able to balance energy flow from one form of energy to another, we do not know which direction the energy is flowing in. And so that's where the second law comes along to help us. So it helps us with determining the direction in which energy will move in a process, and it also helps us in understanding the efficiency of a process. So what we're going to do now is we're going to take a step back and we're going to consider an activity that I'm sure all of you have engaged in while growing up, and that is we're going to take a look at the activity of throwing a baseball. And it doesn't necessarily need to be a baseball, it could be any kind of ball, but typically what is happening when we throw a ball So here's a person, and there's a ball in their hand, and they're about to throw it. What we normally do is we do a little bit of a wind-up. So there we have a ball that has been thrown, and it has left our hands, and it's going at velocity v with vector v. And I've drawn a red line around the ball to denote the fact that that is our system. So we're looking at a fixed mass system, and we are going to apply the first law to this system. So let's draw out the first law, or write it out. Now what we're going to do is assume a couple of things. First of all, is there any heat transfer to the ball? Well, if we throw it quickly and our hands are at the same temperature as the ball, the answer to that would be no, there is no heat transfer to the ball. Are we doing work on the ball? Yes, we are. We're changing its kinetic energy, and consequently we're doing work. Are we changing the internal energy of the ball? Well, if the temperature of the ball doesn't change that much, we can say no, we're not doing any change of the internal energy. And let's assume that the ball has just left our hands and it's moving through the fluid, the air that we've thrown it through, and consequently the change in potential energy will neglect for the initial stages of the ball moving. So what that leaves us with for the first law is the following expression. We can write that the work done on the system is equal to the change in the kinetic energy. So what we can say is that the work done by throwing the ball So the work done by throwing raises the kinetic energy. So with that, why does the baseball slow down after we've thrown it? So that's a common question that we may ask ourselves. Why would the ball slow down? It has an initial kinetic energy, and we do know that it does slow down. It drops to the earth as well, but we're going to neglect that for now. And we do know that it slows down, and the reason for that is we have air drag on the baseball. And the air drag will slow the baseball down because of the drag force. So to answer that, we know that the answer is air drag. So let's take a look at what is happening as part of having air drag on a ball that is flying through the air. So what I'm going to do is draw a larger picture of our baseball, a zoomed in picture, and we have our seams. And it may be spinning, it may not be spinning, it's hard to say. But the ball, we're going to say, is moving at a velocity v, and it's a vector. And if we consider this for a differential period of time, the distance that it will move is that vector times dt. I'm going to put my system boundary around the ball like we had earlier. So that there is the system. Now at the same time, what's happening, I just said that air drag is slowing the ball down, so we have a vector operating in the exact opposite direction to the velocity, and that is our drag vector, and that is actually what is slowing down the ball. Now, if we're looking only at the baseball, we don't see the fluid flowing around the ball. However, that is the source of the drag. And consequently, if we were able to see the fluid flow around and behind the ball, for example, through flow visualization with a smoke or something like that, what we would find is the flow comes along and then there will be a separation point. And we have these large-scale vertical structures that are in the wake of the ball. And depending upon the Reynolds number, sometimes these are referred to as being the Kármán vortex street. If you go on the internet and you search flow visualization, baseball, you'll find all kinds of really interesting pictures that have been collected in wind tunnels. And you can see visualization of this wake behind the baseball. But anyways, that is the source. We actually have skin friction as well as form drag. Those are the two forms of drag that add together and slow the ball down. So let's go back and look at the first law again. Now we said heat transfer to the ball was 0. We said there is no change in internal energy, and we're assuming there is no change in potential energy. So what we were left with was minus W. Now the work, now on the right hand side we know it's the change in kinetic energy, but let's take a look at the work term. We have a vector acting, the velocity and the drag, and they're in opposite directions. So really what we have going on here is the drag force, and we will use a dot product because we want to determine the component of the drag force in the direction of motion. So that's basically the force times the distance, which is equal to work. The force being drag and the distance being v dt, and we are using a dot product. We can represent the dot product in terms of scalars, or the magnitude of these two vectors. And there would also be a sign in there, but it would be sine of 180 degrees, which becomes minus 1, which cancels out the minus sign, multiplied by dt is then equal to the change in kinetic energy, which we can express at kinetic energy at t minus kinetic energy at a later time, t plus delta t, or dt. I'll put dt there. Okay, so that's what's going on with our process. We basically have the drag force, and it is what is slowing down the baseball. Okay, so the drag force is what is slowing down our baseball. Now what we can say is that an equal and opposite force is acting on the fluid. As the ball moves through the fluid, it is acting on the fluid or the air behind the ball. So the equal and opposite force acts on the fluid behind the ball. So the next thing that I want to do, we're going to consider more closely what is happening within the fluid.